then what's after the set of integers? No, there's something between reals and integers. We have two different breakdown of sets from there. It's called rational numbers, which means you can represent it as a fraction. It's going to be your integers in addition to fractions. So I'm going to put in here the integers. If it's the integers, that means that it's also the whole numbers, which means it's also the natural numbers. So we have fractions. If you can write it as a fraction, we also have numbers that are represented as decimals. So I have to think of, okay, now how do I know if I can write it as a decimal? It would include repeating decimals, because repeating decimals we can write as a fraction. So 0.33333333333 is known as 1/3. 0.6666666 is 2/3. 0.111111111 is 1/9. So we can write repeating decimals as a fraction. We can also write terminating decimals as a fraction. So terminating decimals, if I say 0.25, that's 25 out of 100, which can be written as 1/4. 25 hundredths. Reduce it, you get 1/4. So if it is terminating, means that it has an ending spot, then we know we can write that because you put the place value of that last digit. Put the number after the decimal point over the place value of that last digit. All right. And if it's not rational, it is irrational, which includes, or which is the non-repeating decimals, which the non-repeating decimals, if you think of it, would be pi e square root of 7, square root of 2, and things like that. Even though you get a value when you type them in on your calculator, because your calculator is only set to maybe 9 places, 9 digits. All right, and then the classification of all of those is known as the reals. But then we also have something known as the imaginary numbers. What are the imaginary numbers? What gives you an imaginary number? Nope, not quite. That would be up here. It's the square root of a negative number. I'm just going to put the symbol. So the square root of a negative number leads you into an imaginary number. If I gave you, for an example, the square root of -7, that would be written as the square root of 7i, because I means the same thing as -1, or the square root of -1. Now I could say I have the square root of -4. That's equal to the square root of 4. A negative underneath the radical sign turns into an I, and the square root of 4 is 2. So it would have a value of 2i. Those are imaginary numbers. That leads us into another classification of numbers called complex numbers. And a complex number is equal to a real number plus an imaginary number. When you group them together, that's what you're going to get. It's a complex number. So we have all of those classifications of numbers. Now what? It can be under both, because you could say it's 0 plus 2i, which then turns it into a complex number. Just like when you talk about polynomials, you could say 4 is a polynomial. That's the same thing as 4x to the 0 power. We just don't always show that real number part. Normally, you will see it classified as just an imaginary number, but you could, if it's imaginary, it'll be complex. But normally you'll see it classified as the other, just because it's missing. If that real number part is 0, you don't write it as 0 plus 2i. You could. We normally don't do that. Just like if the coefficient's 1, we usually don't write that coefficient of 1. Okay, but what is new? Oh, no. Okay, so we look at the set. All right, you have already worked with some set notation. So I'm on the top of page 3. Right there. You just finished reading to the top of page 3, right? You read the first 2 lines there. Okay, so page 3 says the use of sets. Some of the vocabulary and symbolism associated with the concept of sets can be effectively used in the study of algebra. A set is just a collection of objects, and the objects or whatever is within your set are known as members or elements of the set. So when we come back to all of these sets that I have down, and if I asked you what are the members of the set of whole numbers, you would say 0, 1, 2, 3, and keep on going. If I ask you what are the elements of the set of whole numbers instead of the members of the set, it would still be 0, 1, 2, 3, and you continue on with that pattern. So each one of these entries here is an element or a member of that set. And we use braces, which you know, because clear back in Algebra 1, I'd take off if you didn't show those braces, and you tried to put parentheses because everybody didn't know how to make braces yet. Remember?
I just use parentheses.
So what they have down for you is they have a way that they represent it, and they say a word description. Oh, first of all, and when you name a set, you can use a capital letter. So they say set A is equal to, they say the set of vowels, or how do they say it? Vowels of the alphabet. I'm just going to put vowels. Okay, so that notation right there is what they say is word description. I'm telling you what it is. It's the vowels. Well, we could be more specific, and we could do a list or roster description. A list or roster description would say, what am I going to put in there? What are those members that are vowels? A, E, I, O, and U. There's the set. But then they get into saying that we could use a set builder notation. And this is one when at the beginning of the year we talked about domain and range. And we could say X is the set of, or such that X is an element of the real such that X is something. We talked about how you can say that. This one, we are going to say X is a member of the set such that X, oops, X is a vowel. That's the set builder notation that we have. But then if you also talk about what we looked at when we start talking about interval notation, then we were using the parentheses and the brackets, which we'll get into that later on. But right now they're just talking about that as a set. Are you okay with that notation? All right, if you continue reading there, what they're going to talk about is they're just going to give you the classification. We have natural numbers, and they say natural numbers are also known as counting numbers, but they add to that, they also say it's the positive integers. 0 is neither positive nor negative. So that's why when they say positive integers, it's just 1, 2, 3, 4, 5. If you look at the next one where you have 0, that's the set of whole numbers. It's also what they say is the set of non-negative integers. Negative integers are -1, -2, -3. So if it says non-negative, it does include 0 and then all of the positive integers, because 0 is non-negative. And then they give you the set of negative integers. They show you a set of non-positive integers. 0 is included in that because 0 is not positive. And you have integers. Okay, so we're good with that. If you look at the next page, page 4, it talks about terminating decimals, repeating decimals, and non-repeating decimals. Remember, what does this notation mean if I show you 0.27 with a line above it? Repeating. So that means the same thing as 0.272727. You use, that's called the repretend, and the bar is only over what repeats. So if I were to show you 0.27 with just the bar over the 7, that means 0.2777 and continuing on. Are you okay with that? All right, then they get into irrational numbers, and they will talk about that. And then they give you on the next page, page 5, they start to show you a diagram where they look at, I believe, if you remember, clear back when in Algebra 1, we talked about the set of natural numbers, and I drew probably something that looked like this. And then from the natural numbers, if we add the 0, we get whole numbers. Do you remember a diagram like that? No? Oh my goodness gracious. And then whole numbers, if I add the negative numbers, now I get integers. And within the integers, I see that I have whole numbers and natural numbers, right? And then within the integers, if I start to add fractions, I get what is known as the rational numbers. And then if I cannot write it as a fraction, that's over here known as irrational. And all of these together are known as the reals. Well, if you look on your book or on the handout on page 5, they show it as a gobstopper. Everybody know what gobstoppers are? It's a gobstopper because you have that different layers of candy. So they show it more like the earth, and you talk about that core, all numbers. You sit there and you have the whole numbers. And then if you add integers to it, you've added another layer to that piece of candy, and those integers are your negative numbers. They don't even show the natural numbers there, do they? But you get the idea of seeing it in that format as well. Here's where it plays a role, though. If you look on the next page, page 6, the set of whole numbers is a subset of the set of integers. Maybe I should back up. And on page 5, right above that, I want to call it the gobstopper, or almost looks like a model of an atom or something like that, right? But if you look at the paragraph above that, it says the concept of a subset is convenient to use at this time. A set, okay, so if you have a set known as set A, that would be a subset of another set B if and only if every element in A is a member of set B. If and only if. So you're only a subset if all of your members of one set are in the set of the other set. So if I told you this, if A is the set of 1 and 2. Its elements or members are 1 and 2. And if I told you B is the set of 1, 2, and 3. Is A subset of B? Yes, because all of the numbers in A are in B. Is B a subset of A? No. And here's the notation that you use. To show a subset, A is a subset of B. That's what that notation means right there, which is probably good for all those other people too. That means subset. That means subset. Did you get that, Cassidy? Did you get that, Riley? Good notation for you to notice is it says A is a subset of B. That means that every element or member, every number in this set is in this set. But that's what that notation means. If I tell you this, B is a subset of A, is that true or false? False, because not every number here is in there. Subset is the smaller group. So this is incorrect, so they would draw a line through, saying that A or B is not a subset of A. So if you see that notation, just a heads up, that's what it means. Subset just means it's a smaller part of that group. Or equal to it, because it's got the equal sign there. Every number has to be there. So if you look on page 6, are we out of Kleenexes back there? Oh no, you just dropped the box. On the top of page 6, it says the set of whole numbers is a subset of the set of integers. Whole numbers is a subset of the set of integers. All the whole numbers are integers. So that is true. The set of integers is a subset of the set of rational numbers. Integers, right here. They're all within the rational numbers. The next one, the set of rational numbers is a subset of the set of reals. Are all rational numbers classified as reals? Yes, they are. So they're stating those as subsets. Okay with that? All right. Good so far, right? Could you, for me, turn to page 4. Here's what I need you to do for tomorrow. I need you to, on page 12, I need you to do 1 through 10. No. I need you to do 1 through, oh man. I need you to do, yeah, let's just stick with 1 through 10 for tomorrow. And I might add to that tomorrow, but for right now, we'll just stick to the 1 through 10 for tomorrow.